big is the Traeger?
Yeah.
Or how big was my turkey?
Well, the Traeger. I'm sorry. No.
There's small ones and
There's different sizes.
yeah. You can get like a mini one.
A mini one?
Yeah.
Yeah?
But you couldn't fit like that full turkey.
All right, hold
The
on.
one I have is just barely big enough to fit my turkey.
Some of them are really small.
Okay, I have 3:30, so it's being recorded again. All right, so here we go.
Question 2, part B, I think.
Okay, so here's the homework. And I think we covered question 1 last time, right?
Yeah, we're on question
we-
2, part B. We got through A2.
Okay, so question 2 has to do with the wind-driven flow. Is this the one we were on?
Yes.
Okay. So basically we covered part A, but not part B?
Yeah.
Okay, so I'm already showing you part B, so maybe I'll just show you the whole thing and we'll talk about it. All right, so basically this is this kind of question. Okay, if I tell you the wind stress, you can calculate the offshore wind transport. I do remember that we did that. It's about 1 SVERDIP with tau being 0.1 newtons per meter squared. These are pretty sensible numbers for what it's worth. This is kind of what it is off of California. Okay, so then the next question is, assume the wind is blowing over a strip that extends from the coast out to 10 kilometers. Calculate the magnitude direction of the vertical velocity that's required to balance the offshore Ekman transport. All right, so if we've got 1 SVERDIP going offshore, all right, that's the transport. Then near the coast, okay, and it's blowing over. It's going over a distance of 800 kilometers along shore, and there is this width is 10 kilometers. Then basically you've got that transport. That's the area over which the W is happening, right? And so you're going to get a W of about 10 meters per day. Do you see? I mean, basically here, I don't know. And this is the plan view. Okay, so say I'm measuring the transport, and I got this transport going offshore. Now think of this strip that is 10 kilometers wide and 800 kilometers in this direction. So that's an area. And so you divide that transport, which is in meters cubed per second, by that area, you're going to get the vertical velocity.
I got it.
And you should get something like 10 meters per day. And for what it's worth, those are pretty sensible numbers. That's kind of what we see in the mean.
So you didn't bother putting the negative in the denominator because, not the
It's up.
denominator, I'm sorry, in the
Yeah.
numerator because you're recognizing that directionally it's not negative anymore.
I'm not worried about the sign. I'm just going to tell you it's upward because I know that.
Okay, fair.
I mean, you need signs mathematically, but sometimes it's okay just to say, I know what direction things are. I'm just going to say so.
Mhm.
Cool.
And this was just an application in the end of ideas when we talked about continuity and remember all the volume, all those budgets we did.
Mhm.
That's all that's going on here is a mass budget. What's going out,
Okay.
something's got to come in. And that's all that is. So most of what we, when we talked about the coastal circulation, mostly it was just applications of ideas we already had.
Pretty close.
Wait.
And yeah, C was the sketch. Sometimes maybe I should have put that earlier just so the sketch would be helpful. And then, the thing that we're doing right now, it's a paper we're writing right now, is that this onshore flow isn't like it looks where it's over this whole big layer. It's actually right up here.
Right there.
Yeah.
In my other class, I was reviewing things today from the beginning of the semester, and your name was on one of the things. It was like an isopycnal layer.
Here we go. What class?
California Coastal Currents.
Oh, nice.
Yeah, she used one of your graphics.
Awesome.
I almost took a picture to send you, and I'm like, I'm sure that happens all the time.
Who's teaching it? Lahini?
Is that how you say your name? Decima's one of them.
Mora Decima?
And then it's coupled with the head of the department, but
Yeah, Lahini Alawahari.
I was gonna say I'm gonna butcher her name, so I don't wanna.
Oh, they must put on a great class.
It's
I really like them.
incredibly time consuming and amazing, yeah.
Yeah. I think Lahini's been teaching that for a long, long time. And Mora is more recent, I believe.
Yeah, she brings in more biology element,
Mhm.
but they're both great, yeah.
Yeah.
Anyway, sorry to take up time.
Professor Alawahari's a chemist.
Yeah,
Yeah.
she definitely is.
All right. This one. Oh yeah, this one. Okay, so let's see. I think I've given you that much, and then here we go. This is the Hogmiller plot of. This is from. So this usually I update this every year and give you what's happening this year. But this year, remember I said it's like
so
boring?
boring.
Yes. So I didn't want to do it. So I kept it the same one as last year. Because last year we were having an El Nino. And so this is actually what it looks like. Basically, you have these series of Kelvin waves starting early in the year, bringing warm water across the ocean from the west to the east. And so these series of Kelvin waves, that's what happens to set up an El Nino. And so basically this was a little problem to have you think about that. So first, what is the speed of the warm anomaly that propagate across the Pacific in August? So there it is. That's in August. So here's the problem. Take this information where you can measure the distance it's going at the equator and the time, and you can kind of, make a measurement. See, there's about a month, right? And how far does it go in the month? And go ahead and do that. So there's a distance and a time. See what number you get. See how it compares to mine.
You said a month total, right? Or
Well, in August, see these.
You said August. I took that to mean a month total. I think it looks more like 2 months now.
Yeah, it takes 2 months, but
Yeah.
this is a straight line, so it doesn't matter where you do it. For me, I'm going to say, okay, it's about there at the beginning of August, about there at the end of August, and it traveled from 170-ish to 130-ish. So you can go ahead and, come up with something. You have this in your homework, right? You can take a look at your own version. But basically, how many, so that's 30 days, and this is, all right. Okay, so these are 10 degrees. So 1, 2, 3, 4, 5, 6 ish. So 60 degrees. This is at the equator. Cosine of the latitude of 0. Remember so that's going to be 1. So what's a degree of latitude or longitude? This is longitude, right? So degree at the equator, they're the same. A degree of longitude and a degree of latitude. Remember what it is?
110.
Yeah.
111.
111 is good. 110 is fine too. It's about 111
Is that meters or kilometers though?
Kilometers.
kilometers for sure. Another way to remember it is it's exactly 60 nautical miles. So that helps to remember what it might be in terms of kilometers, even though in miles to kilometers. About 111 kilometers times, what was it, 6-ish, over 30-ish days. And then you should get a speed. And did I don't know, do that in meters per second. So we can do it on the board if anybody wants to. Or you can just say what answer you got.
We got 2.56 meters per second.
It sounds plausible.
1.23.
Hmm?
1.23.
1.23, well, you're off. You guys are off by a factor of 2. How could that be? Should I peek at what mine is? I don't remember what I got. I don't want to influence anybody. I'll show it to you. I want us to do, it's better to do it yourself and then, okay, I know which one I agree with.
I got 2.6. Shit. Oh, sorry.
So we have two 2.6s.
Oh, I got 1.3. So it's like a 50-50 split right now.
We got two 2.6s and two 1.3s. How could you, how could,
I got 2.5.
Well, look at that.
Look at this guy. We messed up. I have no idea.
anybody else have votes in on this one?
Yeah, it is. I'm just gonna.
So it's 60 degrees times 111 kilometers per degree
Yeah.
times 1,000 meters per kilometer. So that's going to get in meters, divided by 30 days. And a day is 86,400 seconds.
Hours, 3,600 seconds.
Yeah.
Yeah, same, so.
So what was the answer?
I got 2.57.
Yeah, so
Yeah.
2.6 to two figures?
Meters per
Good.
second.
Meters per second. I agree with that.
Well,
I did 60.
oh wait, that's better too.
Did you do 60 miles instead of 111 kilometers after all of that?
Yeah.
Okay.
Oh.
Yeah, I said 60 miles. I confused you. That was my fault.
No, it's definitely mine.
Okay, so I agree with that. 2.6 meters per second.
Wait, what was the number?
2.5. It's supposed to be 30. Yeah. I don't know.
I did do that.
30 days and then what?
1 month. Huh?
And then what? Yeah, and then
3 days for 1 month.
what did you do?
I did 8 months.
8 months.
What?
Why did you do 8 months?
Let's just get rid of it.
Yeah.
No.
Okay. Should we go to the next part?
Yeah. I couldn't find a specific speed for,
Oh, here, let me show you. So sometimes in my homework, my goal is to get you to look back at the slides. So
oh no, look at this, I mean.
I know. I know.
I rewatched the video.
So this is the equatorial, this is the last lecture.
Oh, that's why, I was looking in the wrong place.
So it's this.
This is the Enzo lecture.
Yes. So I said, you know, looking at this, it's about 2 meters per second. So that 2.5, or 2.6, it's not so far off. Pretty reasonable. It's a sensible number. All right, so let's go to, hang on a second. What's the rest of that problem?
It's
What is
what value of the quantity delta rho over rho naught each would yield a phase speed equal to the observed propagation speed.
Oh, okay, yeah. I just want you to, oh shoot, it got mangled in here, didn't it? Totally mangled. Is it mangled online too? Is it mangled for you? That's awful. Sorry, it got mangled. Is it mangled for you or just for me?
I did it seems to be wrong. I'm trying to find the video. And then, well, not the grade because you divide it. Oh, yeah, it's like the time, but.
Sorry, mine's going really slow.
I think it's not mangled online. I think it's just my,
Nope.
it's not mangled, right?
It's fine.
Yeah. Okay, it's not mangled here. All right. So this is what we've got, right? That C equals root G prime H. Okay. And here's what I'm hoping you might think about. So if C equals root G prime H, so C equals square root of G prime H, where G prime equals G delta rho over rho naught, right? So let's plug that in. Let me do it C squared. C squared equals G delta rho over rho naught times H. Can you see this one? Can barely see it.
On this side, yeah.
Oh, sorry. Let me write it over there. C squared equals G delta rho. Do we have any more? Are we all completely out of chalk now? So I'll write it here. C squared equals G delta rho over rho 0. Okay, so that's what I suggested in class. And we just found it to be, this to be 2 meters per second, C. And you know G, so you should be able to figure out what this is. I think is that what I was asking you to do? I think. That's what I was asking.
Do you want us to use the 2 for C or our value that we calculated?
Good question.
Oh yeah, which one did I suggest you
Just
use?
set to the observed
Fair enough. Let me go.
The observed one.
So then
So
our,
not the calculated
Um,
one, so probably 2, yeah.
Oh, observed. Yeah, so the 2.6.
okay.
Yeah. Yeah, so for the 2.6, what would you get for the delta rho over rho times H?
Is this one B?
So we're doing part C now, right?
Yeah. B.
B.
B. Didn't we just do B?
No, we didn't
see.
Oh, B, I just said how do those, basically you calculated the 2.6 and I asked you how did those compare?
Yeah, okay.
And you'd say, oh, they're pretty close.
That's it.
Yeah.
Just say them pretty close.
Yeah, what did I say? Yeah, I just said what the phase speed was, I just wanted you to, I was trying to get you to look back at this slide and write it down. So, it's just,
0.69?
so what did you get?
0.69.
That's what I got too. There's my answer, 0.69. And then refer back to the section of potential density along the equator from lecture. Choose values of delta rho and H that are reasonable and yield the propagation speed from part C. So choose a delta rho and a H that get you that 0.69 by eyeballing that one. Like, basically, they're pretty close to these, but you can eyeball it, and if you said, oh, okay, I'm kind of buying that 100, you can figure out what delta rho would have to be exactly. So I'm just trying to get you to look back at this and kind of think about how you might choose an H and a delta rho.
Can you show me your previous equation again? I gotta
Yeah.
look at it.
Well, there's everything. What did I say? I said, well, if you pick a delta rho of 4,
I see what I did wrong.
then I'm going to get an H of about 177. And I don't know, I mean, it's close. Just trying to get you to think about these numbers a little bit.
You don't have to do that.
I was talking about part C. I just made a stupid mistake and
Mhm.
tried to, tried to solve for the wrong thing.
Mm-hmm. And I guess go ahead.
We're looking at which things to figure out rho and H.
Okay, so basically, yeah, this is basically what I was wanting you to do is think about this. This is basically it. I'm looking at this and I'm going, okay, I'm contouring this. What happens? Oops. Okay. What are we looking at? We're looking at basically the thickness of this layer and the difference from in that layer to outside of it. It's a very simple model. The model would be just there's two layers of one of some thickness and then some density difference across.
Oh, okay.
So the way I'm really thinking about this is there is some layer, that's H. There's rho 1 in this layer, rho 2 in that. So delta rho equals rho 2 minus rho 1. That's the model that leads to this equation. But the real world looks like this. And I just want you to look and kind of decide, if this is a model, could you actually read this and get numbers that you might even be willing to accept? Okay, so let me go back to yep. So that's my
So is
solution.
it just mostly trial and error?
It's just, what did I do?
Yes.
I just said, well, suppose that's 4, what am I going to get for H? I'm just trying to get you to think about the size of these. It's not, it's not,
Because if you did like 100 meters, and
then you would get a different value for delta rho.
yeah, you get like 0.175.
So you get 0.175? And so then I guess the question is, would you buy that as even close? So that's basically 2 contours.
0.175 is 2 contours?
Wait, it's not 0.175, it's gotta be maybe 1.75?
It's just not even possible if that was the.
Oh, really? I don't think so. Because 177 is just basically about twice that. I mean, wait, what, use 100, so basically, I don't think it's that.
Oh,
I
hold
don't
on.
think you got, I
I
think you
messed
got
up
a
again.
decimal wrong.
Yep.
Anyways, this isn't the most carefully worded question. I'm just trying to get you to look back at this and think about it a little bit.
Oh. No, now I am curious.
Okay.
So
Do it on the board. I mean,
for row knot, you would have.
let's do it. Oh, here's some chocolate. Okay, so we decided that this is, do we agree that this is 0.69?
Yes.
Yes.
Okay.
First school.
Okay, so now here we go. We got the delta rho over rho naught times h equals 0.69. We got that.
Yeah.
We good there?
Mm-hmm.
Okay. Rho naught doesn't really matter, but let's take 1,000, say 25. That doesn't matter much. Okay, so that means that delta rho times h equals 0.69 times 1025. What is that?
Yeah, 707.25.
7, 0,
7.25.
So then if your height was 100 meters, you'd have 7.07 as the delta.
So let's see. So if your height is 100, yeah, you're gonna have like 7.
Yeah, but that doesn't really make sense, does it?
So I think, what's wrong here? What's wrong? So if, what I got is I think it is like I think that's about right. Yeah, I think that's about right. What I did is I said, suppose delta rho is about 4, then I got H is about 177. Is that about right? Is that what you got? Yeah. And so if this is 100, this has got to be increased by 1.1 3/4. So yeah, about 7. I think that's right.
But you don't see that on the map, do you?
Well, go ahead and read this. Like, what do you see here? Oh, that's so that's about.
Because that's like 2.5.
I mean, it's hard to read these off the map, and it's hard to read them, and it's just rough, and they're at least plausible, right? What is the number you got? 7. We got
7.07.
All right, so let's count these. These are 1. So 1, 2, 3, 4, 5, 6, 7. It's kind of there. It's not too far off. I mean, this isn't an exact calculation. I'm mostly trying to get you to look back and just see. At least it's generally plausible.
Oh, I'm very much looking at a different potential density plot.
Oh.
Right, that makes sense.
It's still on the.
Are you? Okay.
Solid.
Yeah.
Cool.
Okay.
I'm glad we solved that.
Okay. So it's at least plausible.
There we go.
Yeah.
No
At least-
problems here.
Okay. All right. I mean, I was just trying to get you to look back at this slide. That was all I was trying to do.
Well, it made me think, so that's good.
Good. Yeah.
That's the point of the homework, yes.
Yeah, that's the point. Just to get you to look back. Okay. What's the next one? Swells in the open ocean. Okay, this is awesome. These are the kinds of questions I could ask on finals too. All right. Okay, formula for deep water phase speed. Okay, what am I trying to do? Go back, look at the slide that's got deep water phase speed on it, and write that down. That's step 1. And then the next thing, since I'm asking you to do it in terms of wavelength, L, I need you to know what the relationship is between wavelength and wave number, because I probably only gave you the dispersion relationship in terms of things like wave number. So that's it. So that's going to be, the answer here is going to be a formula. It's going to be an expression. Do you want to give it a shot first? You just want me to show it? Give it a shot?
What's G over?
So let's let's look back. Let's look back at the waves homework. Waves lecture. And I was asking for phase speed?
Right.
Yeah.
Okay.
It's
So
just C equals L over T.
so was I saying deep water waves?
Yep.
Oh,
So there it is.
G
So there's a lot of ways to write it, and in this case, the way to write it that I think would be most helpful, because I'm giving you wavelength. I'm asking for wavelength.
Yep.
Yeah.
Okay, so that's the most convenient way to write it, I think, in this case, would be that C equals root over GK. You see that?
Yep.
Okay. What's the relationship between K and L, if L is wavelength?
2 pi. 2 pi.
Right, so how do I write that? K equals, or
2 pi over L, or you can just write C is equal to G and L is square root of G and L over 2 pi.
yes, put it in there, there's your answer.
Well, for the phase speed though, wouldn't you have to, oh wait, this is the, I thought it was asking for the group velocity.
I could have asked for that.
But you didn't.
I'm just trying, again, what is my goal here? My goal is to get you to look back at this and spend a little time
Yeah.
with, staring at the results, the stuff from the lecture. That's my objective.
You didn't want that solved
So
in
just
terms of L, like L equals?
Yeah, I'll show you what my solution is, and you can, basically, I want something that looks like that.
Oh, that's literally, okay.
Yeah. Because it's C in terms of that.
buckets.
I mean, almost always I'm gonna write things this way, but I'm just trying to get you to look back, and I just want you to,
Make us
I want
work
you to
for it.
spend time with this stuff. That is my goal. Spend time with it. Because the more time you spend with it, the more likely it is you'll remember it. Okay, same thing, but doing this in terms of wave period. Then I would probably use this other expression for C, which is that it's equal to G over omega. again, and I'd like you to understand why we can write it both ways. I want you to kind
Especially
of,
for the following questions.
yeah, I just want you to spend time on this. It's my whole objective here. And then again, omega is equal to 2 pi over t, where t is the period. And did you give that a shot? You should get an expression. Tell me when you're ready.
Ready?
Ready?
Yes.
There we go. Just trying to get you to spend time with it. Okay, what's the next one? Dispersion relation. Same thing again. Spend a little time. What's the dispersion relation? Actually, this dispersion relation I can remember because I know that it's just depends on G, and I need an omega and K in there. So even if you didn't have your cheat sheet, which you will have, so you will be able to write it down, if all I know is I've got omegas and G and K, and I got to get something that equals, so what's it going to be? I just know it, but basically omega squared, that's got units of 1 over seconds, right? Here's the way I'd actually do it. I'd go, okay, let me write G. Okay, G's got units of meters per second squared, right? What am I going to do to get this so I can have some G's and omegas in there? So, I mean, omegas and K's in there, so it's going to be equal to something. And I think, look at it, go, if I multiply that by a K, that's got units of inverse meters. Then that's going to have units of inverse seconds. So that must be the dispersion relation.
That's such a good idea.
And it's pretty much nothing. Now, this isn't perfect, right? Because there could be factors of 2 and stuff. But in this case, I know there's not. So I don't ever have to memorize the deep water dispersion relation. I just know I can figure it out because I know there's no 2's. But for the group velocity, there is. That's it. Same actually goes for the, like you don't actually have to write down to remember the dispersion relation for shallow water waves either, right? And this is why. So for shallow water waves, I know they're non-dispersive, and I know that it's just going to have, it just depends on G and H. So all I got to do is remember the phase speed. So if I got G, that's got units of meters per second squared, and I need to get something that's units of meters per second out of that. All I got is H. Well, shoot, I should multiply by H. And then I need to know I have to take the square root of that, and that's going to have the right units. And because I know, I remember there's no factors of 2, I'm pretty good, and I'll never have to memorize this again in my life. And so then, because it's non-dispersive, the dispersion relation is just that. Did you get the dispersion relation? I mean, it's not a beautiful expression, but there it is. Maybe I shouldn't have asked this question. I mean, anyways, but there it is. Just want you to spend some time with it. Okay, what's the next one? Now something that we actually would do. What is the wavelength of a wave of period 10 seconds? Because you've got the dispersion relationship. Now you can just stick 10 seconds in there and you can get L quick. And this is relevant for people who surf. This is, I think it makes you a better surfer to know about waves, wouldn't it?
That's all that's the hardest part. Figuring out where to be in relationship to the wave. Yeah.
So, I mean, this is something you should know. Like, what's the wavelength? If they're 10-second waves, you should know it's, well, so you know its wavelength out in open ocean anyways. Once it gets into shallow water, it changes. So what wavelength?
156.1.
Yeah, 156.05 meters.
I got 156.
So I got 160. I'm just going to 2 figures. I just did 2 figures. I'm sure you're right.
it's gotta be my calculator, because I have the exact same thing, but my calculator is always off. It's just a
What, you
small
said
fraction.
156, didn't you?
Yeah, 156.
Yeah, well,
Oh,
I'm
but
just
you
doing it
have
to two figures, that's all.
Gotcha.
I'm just doing two figures. It's okay. I just did two figures, but 156 I'm sure is probably right. Okay, what's the next one? Phase speed of a wave of period 10 seconds. So we already have the phase speed in terms of period, so you plug away.
15.6.
That's what I got.
That's what I got.
Yep, 16 meters per second. There you go. And so this is relevant for surfers, right? Because now you know how far apart the crests are and how fast you're going. 16 meters per second. What is that in miles per hour?
It's pretty decent, I think.
I actually, what is that? I should,
15
let's see.
times
So,
faster than the Gulf Stream.
oh yeah, it is. It's a lot faster than the Gulf Stream. So in round numbers, it is about that 1 knot, so 1 mile per hour, is about a half a meter per second. So a meter per second is about 2 knots. So multiply that by 2, that's 32 knots. That's about 32 miles per hour. It's actually faster than 32.
That's
Isn't
what
it?
I bounce when you hit.
So that's why it's fun to surf.
Yeah.
Because you're going fast. That's open up. Things are slowing down. They're slowing down. By the time they get into shallow water, they're a lot slower. But 16 meters per second is fast. Let's book it. What's the number I remember? Let's see, 60 miles per hour is about 80 something feet per second.
What's, I looked it up. Are you still talking about 15
Yeah,
meters per second? It's 33 miles an hour.
yeah, yeah. I said 32.
Did you?
Yeah. So yeah, you're going fast into an open ocean.
Faster than when I set a school zone.
That's why surfing is fun. If you're going, surfing wouldn't be fun if you're going
2
slow.
times the speed of killing a small child.
Yeah.
I mean, there's other parts of surfing that.
Illegal in a school zone?
I mean, you know what you're doing when you're surfing, right? I mean, you're just going downhill, right?
I've never been to.
You're skating on a
Well,
less reliable surface.
Basically, you're just always, it's gravity, you're just always going downhill, but you kind of time how fast you're going and adjust your friction so you stay on the face of the wave. But you're basically just always going downhill.
I like saying.
Okay. Always going downhill.
I feel that. I feel that, dude.
Okay, so let's do the next one. Particle motion at the of a wave
6.28.
Yeah, I got 6.3 meters per second.
for the particle motion.
Yeah.
Yeah. So basically, it's a circle. You know its circumference. You know how long it's going to take. And then how do you compare? How do those two compare? And this is really interesting. So the phase speed is a lot faster than the particle motion, and that makes it that's interesting because when these start to become the same as the wave gets into shallow waters, when you get all these nonlinear effects and breaking. But outwards, whenever this is a lot bigger than this, that means the waves are pretty linear, nice, simple sine waves. But that's if you took a waves class, you learn about stuff like that. Okay, what's next?
The frequency.
Okay, we did this in class, so I'm not going to do it again. Right? We did it in class. Totally.
About it.
So, and then, so this is the last one that we have to cover today. Okay. These are just like you think it through, and give the answer.
Draw a really pretty picture for you.
Oh, did you? Good.
I really drew.
Oh, good. So, which is the answer?
C.
Okay. Spring tides occur twice each month at full or new moon, right?
Yes.
And so why is that? Part of this is explained. I mean, I'm not going to make a big deal about it on the homework, but give a brief description because this is going to help you to remember why, and I'll ask similar kinds of questions on the exam. But
I'll buy it.
yeah, but why? It's because they're in line. Yeah,
They both influence, right? Like,
and they're pulling in the same direction.
yeah, and it's additive in that.
Yep. Okay, what's B? The daily inequality vanishes for lunar tides when one of these things is.
A.
Yep, A. You know why? Be able to.
Diurnal inequity for difference in elevation.
And then finally, neap tides occur when?
A.
So sometimes occur at the times of eclipse, only at the eclipse, or never at the times of the eclipse. A neap tide.
I thought it was B.
Isn't it B because it's off axis?
It's never going to be. See, at the time of the eclipse, that's full or new moon.
When they're
Yeah,
aligning.
when they're aligning.
So that would be more
So the
spring
neap,
time,
it's
yeah.
never going to be at the time of an eclipse. Not ever, never.
Who's at the top?
Yeah.
That's always.
I think it's A.
So,
Wow. Cool, because I was reading like my explanation again, and I was like, wait, this kind of sounds more like it's B.
so I didn't do my own drawings. I just told you what slides are on in my mind because my drawings wouldn't be any better than what are in the slides. But if it helps sometimes to draw stuff yourself. So please feel free to do it. That's it. That's everything, and we are done with a few minutes to spare, so you can refer back to this.
Last homework.
Last homework, last.
I'm gonna go sit in traffic for a while.
Oh my god.
You have to go sit.
I get to go sit in traffic for the next hour just to like immediately leave 10 minutes later.
I gotta go back and do a Zoom from 5 to 6.
Oh, that's not that thick.
I had a question
What
about.
could be worse than a Zoom?
Are you at home or the office?
I can't get home but I live in North County. I can't get
Oh,
home.
yeah.
So
Never mind. I take it back. That's pretty bad. Especially since you have to stay here till 6 p.m.
yeah,
But you might need some rush hour traffic.
traffic should be less by 6.
I usually go home at
I find 6:30 is the sweet spot.
Where do you have to drive?
6:30, I drive to the end of Carlsbad.
Okay, so you're going the same direction as me. Yeah, yeah. I often wait it out, but I
I'm
actually
over in La Mesa. It's just bad.
I like riding my e-bike more, but it's
Here?
I ride here from Encinitas on my e-bike.
Oh, okay, that's, yeah. On your e-bike. I thought we were talking about Carlsbad. I was like, you're crazy.
Well, I'm in Encinitas. It's just Carlsbad's just one more click.
Yeah. That seems, I've seen people go down on their bikes, like the city bikers. No, from Encinitas to UCSD.
Yeah, I'm just
When I
riding.
take the bus, or if you give up, just get on the bus.
Last time I tried to drive my bike down there in my car was.
Yeah, I guess Torrey Pines isn't as painful if you're on an e-bike.
Well, no, the cool thing about, like, I ride a bike too, so, but the thing about the e-bike is it evens it all out,
Yeah.
right? So the hills aren't as brutal,
Yeah.
and the downhills are the same, so, yeah. It's just that this time of year it gets dark so early, and I don't like riding at night.
Do you ever use the train to commute? I was talking to somebody.
I tried it, I gave it like a solid 2-week try, and I couldn't pull it off. It takes so long.
Yeah.
It's not the train part is awesome.
Yeah.
It's the getting to the train, and especially getting from the train to here.
Yeah.
It's brutal.
Oh, yeah. What is it close, like Solana Beach is the closest one here?
was
No,
trying
it,
to figure
you
it
get
out.
off in Sereno Valley.
Really?
That's where, and that's the closest stop, and then there's a shuttle from UCSD, and then that takes you to somewhere on campus, and then another shuttle to get down here. So by the
Yeah.
time you do all of those things, it takes an hour and a half.
Yeah, I'm only in Claremont and I was trying to figure out bus routes just to avoid parking, but same argument. It just wasn't worth it.
My friend just bikes, she lives in Claremont also, but she lives right next to the trolley station. So she just will bike down, she's so lucky, she has like a 1-minute bike ride down a hill to the trolley station. And then she's just like on campus.
Oh, that's nice.
Yeah.
Yeah, the trolley's better than the coaster.
Yeah.
Thank you so much, Professor.
Thank you.
It's been a serious pleasure learning from you. Like, I cannot believe how much you were able to pack into 10 weeks. I can't even believe how much we learned.
Great,
Well done.
I appreciate that. Thank you.
Thank you.